Greetings everyone. In this video, I'll be walking you through a practical implementation of modern portfolio theory using Python. This is a quantitative method to determine the optimal allocation of assets in a portfolio with a goal of maximizing return relative to risk. So before starting further, let us know what is modern portfolio theory. So modern portfolio theory is a foundational concept used in finance to help investors to construct portfolio to maximize their return for a given level of risk. This theory emphasizes on diversification, which means combining assets of different risk return, for example, shares or equities, bonds, debentures, treasury bonds, etc. In this way, an investor can build an efficient portfolio that lies on efficient frontier with no portfolio offering higher expected return for the same or the lower risk. So let's start now. And I would like to say the first and the most important thing is to import the suitable libraries which will be required. For example, as you can see my screen, import yfinance, pandas, data time, numpy, scipy, thread API, etc. So these will be used. So how can you do it? You can go to window plus command. So this will be a run tab over here. And when you click on the command prompt, there will be a command like this. Uh, a tab will be opened. And here you write pip installed yfinance. I won't do it since I have it. But if you want to do it, you can first install these all and then we can start further. After that, in the section 1, we will define the tickers. I've used 5 assets such as the SPY, the BND, the GLD, the triple Q, and the VTI, representing US equities, bond, gold, and broader market of ETFs. We have also downloaded the data for the 5 years using the Y Finance library. In the section 2, when we come, in this part of the code, I'm setting up the time range for my analysis. I use date time today to get the current date and then subtract 5 years using the time delta, which you can see as days equals to 5 multiplied by 365. This means that I am pulling 5 years of historical data for each asset, and then I create a data frame to store the adjusted close prices for each ETF. Using uh, using it, I go through each ticker and fetch its data using Yfinance. If the data exists, then I use close column and I add data frame. This step ensures to have a clean data set of closing prices for each asset, which I'll be later used to calculate the return and risk matrix. Coming to the section 3, once the prices are loaded, we calculate the logarithmic returns, which are returns which are situated for the financial modeling due to their additive and compounding nature. After this, we analyze the covariance matrix. So before going, let me tell you what is covariance matrix. This is this is the way the assets move in relation to one another, and it is essential for measuring the portfolio risk. This also helps in understanding the overall risk when combining all assets together. After we have calculated the logarithmic returns and the covariance matrix, we go to the key performance matrix, that is the expected annual return and the portfolio deviation and the Sharpe ratio. So the expected annual return, this is the average return I expect in a year based on the historical performance of the portfolio. Expected volatility, This shows how much returns are likely to fluctuate. This represents the portfolio risk. After this comes the Sharpe ratio. The Sharpe ratio is the measure of the adjusted risk adjusted return. It tells how much return I'm earning for each unit of risk I'm taking. A higher Sharpe ratio means generally a higher uh, return you are getting on your uh, investments. In the section 6, we fetch the current 10 years US Treasury rate using the Fred API as the risk-free rate, a necessary input for the Sharpe ratio. So why actually I use the Sharpe ratio over here? I use the Fred API. Well, the reason is simple. Since it gives me the um, accurate increase or decrease uh, in the portfolio or the investments that are being placed. So you can see here the portfolio optimization sh- which has been shared. So generally when I read finance textbooks, so in that the average risk-free return is 0.02. So if you have to write, we'll write it as that 0.02. But for if you want accurate result, I would say you use Fred API key. So how you can get this? You go to the Fred API over here and then you log in, you request for your API key and then it will give you one. After this, then we use the scipy optimize minimize function to optimize the asset weight, which with the goal of maximizing the Sharpe ratio under specific constraints. Like, for example, if I tell you over here the constraints and bounds, this one. So in this particular, we are able to see that the summing that the weights are summing to 1 and being limited to 0 to 0.5. So this output shows the optimal weight or the expected annual return, the portfolio's volatility, and the final Sharpe ratio. These values guide us towards a theoretical optimal portfolio based on the past performance and the correlation among assets. I also maximize the Sharpe ratio, which runs the optimization using the SLSQP algorithm. The goal is to maximize the Sharpe ratio and minimize, or in a technical term, we minimize the negative Sharpe ratio. Uh, in the next part, now coming to the next part, it is constraints, which represents the sum of all assets weighted must equal to 1. Over here, we could see that the constraints are equal to 1. And secondly, the bonds. Bonds refers to the each asset class that can be weighed between 0 to 50%. The limits over exposure to any single asset, keeping the portfolio diversified. Then I set the initial weights where each asset starts with the equal allocation just as a neutral starting point for the optimizer. Finally, I extract the optimal weights from the result. These weights represent the most efficient allocation for the given risk and the return profile. In the section 7, which is the last part, finally we are have completed. However, this is a very uh, boring code. So what you can do is you can just type this, and when we go to the terminal, I'll set a new terminal once, and when we click on the run, we are able to see that it is now processing all the data together. Yeah, it is being processing as we can see. So finally, from this, we will be able to visualize a bar chart of the optimized portfolio allocation. Now, if we see this, so we are able to conclude that the SPY and the GLD has surpassed then the BND and the QQQ and BTI. Why has this happened? This is basically due to the as it has expected the return then or has expected more return than both of these. Okay, so we actually had two, three commands. That's why it's coming. So, as we are able to see over here, the annual expected return is 13% and the expected volatility is uh, 12.5 and the Sharpe ratio is 7.4%, which is, in my say, it's good. And one thing at the end is that, however, our graph will also change due to some bounce and the start and the end date. So this is something that I really like to play whenever I'm free. So if I, uh, change this to, for example, 6 days, and then if I change my bound, where is it? Yes, to 0.7. It comes as then you will able to see that the graph will change automatically. Let me just close this once. Okay. Yeah. So why this actually happened? This actually happened because this shows that how the portfolio, how the MDT is really sensitive towards the bounds and the historical data. So if we change it, of course, we'll get a really uh, a different image. As you can see, that the GLD is at 0.7 and the QQQ is at 0.3, and the expected annual return, expected volatility, and Sharpe ratio has also changed. So it is a very fun experiment and a project that you can actually try. I even, how now we'll actually come, how is it actually affecting the graph? So the first thing that we actually did was the start date. As I'll just tell you what is start date. This is the start date of what we have changed. Yes, this. So this is the start date. Since we changed this, we are able to see that the historical data used for analysis, which is the price returns, has also changed. And the log returns are recalculated. The log returns are the logarithmic returns over here, if we see here. So this is a whole calculation. It is a mathematical or quantitative finance. Therefore, one change or a one numerical change in this project will change the calculation, will change the graph, and it will affect the whole portfolio in whole. We can also see that the effects of changing of constraints and bounds. What are constraints? As I've told you, it ensures the total weight of sum should be equal to one. And bonds is the way how we restrict how much money should be invested in each assets. So if I tell you that zero point 0.5, which was before I had taken, was a moderate. So if this would be 0.3, it would be called that it is tightening the optimizer. That means we are more constrained towards the how much assets, how much money should be invested in those assets. However, if I do it like 0.9 or if I do it like 1%, like 100%. So in this case, it's like it is loosening. Like, okay, now if I do it like one, if we can try, so if I do it like 0.1, so you can see that this will entirely change the graph once again. It is loading right now. It's loading, and we'll see. Yes, look at this. So it has completely changed. Now we see that all of them are at uh, 0 on 100%. So this is what modern portfolio theory is. I hope you like the video, and I'll also share the link of the Fed API and the code for anyone of you who wants to do this project. It is on my GitHub, and you can also have a summary what we have actually taught here. And by this, I would like to end my video. Thank you everyone for your support.